Good afternoon, everyone, and welcome to Advanced Computing and Communication Society of India. In short, we call it as ACCS, which has office in Bangalore in Indian Institute of Science. On behalf of that, I myself, Professor Debabrata, and from IIIT Bangalore, and in full form, we call it as International Institute of Information Technology. As you know, Bangalore is famous for information technology. This institute mainly focuses on information technology, and we have a computer science and W department.
Right.
And from ACCS, I welcome Professor Jan Rabaey, who is an emeritus professor and served 33 years in the Department of WCS in University of California, Berkeley. And he was chair for 2 times in the department, and also made a couple of labs, out of which one of them famous Berkeley Wireless Labs. And I request professors to speak about himself as a CTO of IMAC and also as a professor of emeritus of Berkeley WCS department, and introduce some of the areas what he has been working, then we'll go forward.
Okay, great. So thank you for the invite. Pleasure to be here today. Definitely pleasure to be in Bangalore for my second time.
Oh.
So yeah, let me tell a little bit about myself. As you said, I've been on the faculty in Berkeley for more than 30 years. And my area of interest has always been on the impact of wireless in general on how we as humans and society will connect together. So let me go back a little bit in time. In the early 90s, it became clear that wireless technology would become very important and would become ubiquitous. So together with one of my colleagues, I asked myself the question of, suppose you have ubiquitous wireless connectivity. If wireless would be everywhere, how would you build a computer? Would you still build a computer? And the answer we came up was no, you don't build computers anymore, you build user interfaces. The computing will be done somewhere else, and you carry a device with you, a portable device that allows you to interact with the computing in the background. We called that project the InfoPad. It was a pad-like device with pen input, voice input, and so on and so forth. Remember, this was 1990. Time you had no cellular phones yet. The wireless technology, the best wireless technology available was 802.11, no other characters. That basically gave us about 1 megabits per second data rate. So we built this device, showed that indeed it was plausible. And as always, technology takes time to pick up and before it becomes marketplace, but obviously 10 years later we got iPads and we got smartphones and all these kind of things. But my quest always have been, from there on, the question was, can I make this thing smaller? Can I make it more effective? Can I make it more ubiquitous? So from there on, I moved to the domain of what we now call wireless sensor networks. If I say I can make my radio smaller, can I build a node that has a computer, has a wireless interface, has some sensors, and connect them all together in a large network? Again, we had a set of projects that you can indeed build something like that at a cubic centimeter, and then later scale it down to smaller and smaller sizes. But if you think about it, this led to things like the Internet of Things.
Exactly.
Or Industrial 4.0, the idea that we're going to sprinkle the world with sensors that are connected and connect information, actually connect our cyber world to the physical world around us. So that was the next step. Then around the mid-2000s, say, okay, what happens if I go from a cubic centimeter to a cubic millimeter? What could I do at that point in time?
Okay.
And that brought me into the whole sphere of actually biophysical systems. Exactly. Can I now start having electronics that talks directly to biological cells? I see. It could be neurons, or it could be electrical fields in your body, wearable devices of all style. So it's kind of been a progression of going to smaller and lower power devices, but ultimately extending the application scope initially from pure communication or data gathering to cyber physical systems, ultimately to cyber biological systems. That's kind of the road that I've been following over the years.
It's very interesting. And what I felt is that it has a lot of applications also when you move towards biological
That's right.
cells, like nano communications inside the body.
Correct.
And also the putting the medicines into these nano communications devices, which will carry the from your to the exactly place of your infections and all, leading to that direction maybe. So thank you, Professor, for telling broadly two areas. One is your bringing down the larger wireless communication system to the smaller, and which is now your vision of 20 years back now is IoT people are talking about.
Correct.
And ubiquitous systems, and also the biological systems communication to the wireless. So I will next wanted to know more about your vision towards integrated wireless systems. What you mean by integrating the various wireless systems available, and how you look forward to that kind of areas of research.
Correct. So, so wireless is indeed an integrator. In the past, we were always thinking about individual devices with a particular function. And the function was in the device. With wireless technology, it is possible to have a broad range of devices that are scattered around in the environment to form a network. And the function is not anymore in the devices, but is in the global network itself that provides a function. It provides capabilities of gathering data of different types and nature, but also from different places, combine it together, either centralized or in a distributed fashion, reason about it, think about it, and act. So we are actually starting to make intelligent networks. And this is where we're going. If you think about where we go now with 5G as the next step that's happening, 5G promises two things. On one side, it's going to give us higher data rates. Remember the 1 megabits per second of 1990? Now we're talking about 10 gigabits per second links.
Exactly.
So the types of information you can present and transmit out is going to be so humongously larger that I can start thinking about immersive worlds, that you can think about real augmented reality. All those type of things are going to be possible. That's one side. But the other side is that capability of connecting millions to billions of devices together. Think about a world that is completely filled up with devices connected together, giving us a direct link between, again, the physical world around us and the cyber world, which used to be separate. Now they become one thing. They basically are almost becoming indistinguishable. People talk about digital twins of the world and all this kind of thing. All those things will be possible by this gigantic network of devices together in a ubiquitous way are giving us new functionality, new capabilities. And you go one step beyond that. You mentioned I mentioned the physical world. The same thing about the biological world. With the sensors on our body or around our body or inside our body, we should be able to get a precise vision on how our body is operating.
Exactly.
What is happening that is wrong, helping us to correct things that are wrong, but also give us more functionality, giving us capabilities that we don't have today. You may call it augmentation. But this will happen as a result. And I think this is, if I look forward, obviously we're not there yet. We have to think 10, 15 years forward, but this to me is something that is clearly on the roadmap.
Very nice. So looking at your vision, so can you lead us a little more towards that brain and machines, the interfaces also that, and these 10 to 15 years of research, the roadmap you are talking about, which is very interesting and which will help our younger generation to think about their research areas.
That's right.
So Can you please little deep dive into
Sure.
your thought process into the brain-machine
Sure.
interface?
So yeah, so the first set of sensors that people have been building was about how your bioparametric behavior was. You basically measure heart rate, other things, and you figure out how things go. But there's no reason, again, if I can make my electronics small enough, if I can make them know about the size of a biological cell, I should also have the capability of creating a direct interface between a neuron and an electronic device. So I have neurons in our brain talk to electronic devices, transmit the information out, and use that to do certain functions that I can describe in a minute. So, but really the idea of brain-machine interfaces is to create a channel between our biological computer that we have in our head, create a direct channel that basically allows us to read out information or to write information back, right? So why would this be good? Why do you want this? Well, obviously, the first reason is there's a whole bunch of medical reasons. There's people that have lost motor capabilities because of accidents. Spinal cord injuries, for instance, is a perfect example. You have an accident with a car and you snap your spinal cord, suddenly your brain, which is perfectly intact, cannot communicate with your limbs anymore.
Exactly.
However, if I can read the signals in your motor cortex and transmit them out and help those to either stimulate your limbs, create, or basically help provide or drive a prosthetic device, I can give motion back to people who lost it. Same thing, for instance, with people that have Lou Gehrig's disease. It's a disease that basically makes the ends of your nerves die off. And basically, your brain is now left disconnected from the rest of your body.
Exactly.
There's a number of, one very famous person is this famous physicist, I'm just trying to remember his name right now, who recently passed away, who had that particular disease, and the way he communicated with the rest of the world for 10, 20 years was through small communication movement of lips.
Stephen Hawkins.
Steve Hawkins, exactly.
Yeah.
So suppose now that in his particular case, I could have had an interface that latched onto the speech region, motor region of the brain. You actually can capture those signals and drive them into speech synthesizers. You can make people with those type of disease speak again and communicate with the rest of the world. Yeah. Similar is true for mental diseases, depression, post-traumatic disease. All those type of things could be addressed if I have effective brain-machine interfaces. Now the problem is we can do this. It has been shown. We have demonstrators and people on primates as well as humans that this technology is indeed feasible. However, the technology today is too bulky. It doesn't last very long. You don't want to have a cable coming out of your head and walk around on the street. So you have to make sure it is the technology that you implant that can last for at least 10 years.
Exactly.
Is powered not by a battery. So, and it has to have a wireless interface. So all those factors together requires another form factor in shrinkage, reliability, effectiveness, all those type of things need to happen before we're going to have effective brain-machine interfaces that humans can carry with them for tens of years. And again, plenty of research still to be done, but the roadmap is clear. I'm 100% convinced that you will see technologies like that in a decade from now.
I see. Good. I'm sure your vision in that direction definitely moved because human requirements are moving in that direction. Of course, it will take 10 to
That's right.
15 years.
Because anything you put in a human obviously has to go through regulation processes, approval processes. And again, you want to make sure it's absolutely robust, reliable, private, safe. All those type of things are really important.
Exactly. And moreover that nowadays people are very much worried about the security of the devices connected to the human being because somebody should not hack and do something which harm human health and the data coming out, privacies and all those things. of your
Absolutely.
vision. Your vision definitely will be useful in that directions. So I'll be discussing with you a very interesting area which we have been facing challenges in India, in almost all the top institutions, and also in the world, on the top institutions in the world, from student point of view, because our future generation, which will do research or the teaching and R&D and all those things, they are now going through undergraduate coursework or masters and later on PhDs. So what we found due to this open source teaching materials and the Coursera's, NPTEL of the world, which has a lot of nice videos of the professors on different areas. So students have reduced to attending classes. So this is a phenomenon observed by most of the universities across the globe. So I have a couple of observations, and I also want to know your views, because you belong to, you have a wonderful experience on all the top universities of the world and visited. You are also visiting professor in some of the top universities in the world also. So by not attending classes by the students, do you think they will miss the concepts of the fundamental of a subject? Because the professor, while teaching, he goes deep dive and gives example. So what is your
So you're totally correct. So this is a phenomenon happening everywhere, and it is something that we need to think about. But I don't see it as necessarily a negative thing. Ultimately, the learning experience has changed.
Okay.
We used to get a textbook and you read everything about the textbook, and that's the material you got, and the rest you got from a professor teaching in the front of the class, and have a one-dimensional conversation, a one-directional conversation towards the students. Today, the learning experience comes from many, many different sources. You have textbooks, you have lectures online, you have slides online, you have tutoring, and so on and so forth. So they all together form the learning experience. Now, every student, by the way, is going to learn in different ways. You have people who are verbal, you have people who are visual, that they like to see the video. Some people want just to hear the sound. Some people want to read. So adjusting to all those students, that's kind of multidimensional learning experience, basically helps you to address the broad variety of students you're going to be dealing with. So again, yes, this will reduce the number of students you have that attend your lectures. Now, what I believe a live lecture should be a communication.
I see.
It is not anymore this, here's all my material and I'm going to present it. They can find it online. They can find it by listening to things. It's about discussion. It's about asking provocative questions and getting the students to get engaged in the experience. That's really important. So we have to rethink how we lecture and teach a class.
Exactly. That is an important point you said. Rethink
how
we should lecture in the
absolutely
class as a faculty members.
And absolutely. And then you have to have other mechanisms to make sure that students master the material and what stage they're in terms of understanding. And that could be done to a variety of ways. Obviously, you can do tests in many different ways. Online, you can have little quiz questions, all those type of things. There's a set of mechanism of assessment, how well students are learning. But to me, the life period of time is really about conversation. It's as much about the students thinking about the problem and phrasing their questions to you than us conveying information in their direction. To me, that's the most effective thing. And again, you have to have the different mechanism in place to make sure that they do the different pieces.
Exactly.
For instance, if I have students coming to my class and I say, well, I'm supposing that you have watched the lecture in advance, and they have not, then it's useless, right? They come and they don't have the background. So you could have a little quiz in the beginning, say, okay, you say, okay, you watch this lecture, and then the next time around they show up, and you have a little quiz, a couple of questions about it. So you force them to make sure that they go to the various steps.
Very good point. Means that is a very practical suggestion. That means they should be suggested to go through the concerned professors or on the open source available,
That's right.
or the same professors who is teaching his
That's right.
recording.
That's right.
Then make a quiz. That is important. They should be seriously observe that.
Absolutely.
Then in the class do the conversations and all kind of things.
And we are actually forced to do this. In our introductory classes now in computer science, we have now classes that have 2,000 students.
Wow.
There's no way they're going to fit in a single room by definition. So they're going to have that online experience.
Yeah.
Most of it is going to be online, but you still make sure that every student has the capability and the potential to talk to live tutors, to the faculty, ask their questions. You have to have that human aspect still in there as well. And you have to provide enough bandwidth so that most students can basically do this.
Professor, fantastic point you said. Only for two things I will just clarify more what you said.
Okay.
One is that human interface needed for teaching.
That's right.
It was professor and students previously.
Right.
Now either professor and professor plus tutors.
That's right.
Should meet with the students.
That's right.
In a smaller numbers.
That's
students.
correct.
Okay.
That is correct.
So that means you are again emphasizing that this online 100% may or may not work.
No.
Human interface has to be there.
That's absolutely true. And actually what we do, let's say for those undergraduate classes, we actually have, again, we have, if you want to have this 800 to 1,000 to 2,000 students have human contact, where do you get your tutors? Well, it's your own students. Once you take in the class, next year you can become a tutor.
Exactly.
And this to me is also very important, that students actually by explaining the material to somebody else, they learn the material again. So they get more depth into the understanding. So it's teaching is part of your learning experience. Yes. And having every student required to do some tutoring will help them in their learning experience as well.
I will just try to know from you, which is again a worldwide phenomenon in the teaching. If there is a AI electives or ML elective, majority of the students, 80% or 90% of the students of a master's program or an undergraduate program or PhD program, they enroll on those courses.
Right.
That's fine. That's not a problem because that is needed and that has application. But some of them are misses their core area courses and at an ML AI.
That's right.
So what is your advice to them with respect to ML AI, how important it is and how important it is the core courses, means core according to their areas of work or areas of the programs?
Right. Now, I think again you're hit on an important point. Techniques such as machine learning are important not only to engineering students, not only to computer science students, but actually are becoming important to virtually every student in every discipline on our campus. It might be English, it might be history, it might be astronomy, it might be physics. All of those disciplines have to deal with data, understanding of data, management of data. So rather than forcing all those students to go to the rigor type of, they don't need to understand the whole concept of neural nets and how they operate and things. They have to understand the methods. So introductory courses that are oriented towards other disciplines that help them to learn the basics of statistics, the basics of machine learning, so they can use the tools to basically use the tools for their particular discipline without understanding exactly how that tool operates. That's the right way of going, rather than forcing everybody in these in-depth machine learning and AI courses, which you will never use. Right? So the same thing has always been true with mathematics. Right?
Exactly.
It's the same thing. It was one of those core disciplines. Now, does everybody has to know how to solve an integral by hand? No. Once you understand what an integral is, I can use tools like MATLAB to solve some particular problem, as long as I can formulate the problem and understand what the formulation means.
Exactly.
So basically broadening it out and having the capability of larger population of people getting access to the tools, that is important.
Thank you. Because there are a lot of thought process the young students don't know. They all move
sir.
according to the wind.
That's right.
Today is ML, tomorrow is
That's right.
AI.
Yeah.
Once upon a time, it was genetic systems,
Algorithms
then
and
expert
absolutely.
systems, and
That's
all.
right. Mhm.
But it is important, and for, as you rightly said, and but they have to only learn those particular
Yeah.
things for their areas of interest.
That's right.
the
And then
problems.
obviously you have people who are going to be algorithm developers.
Yeah.
They have to go into the in-depth, right?
Yeah,
If
yeah.
that's true,
Exactly.
I don't have to be able to design a chip to use a chip, right?
So, Professor, my last interest to know about you, because you have written two famous books on integrated circuits, very popular state-of-art books written by you, and it is very popular worldwide. So, what is your vision for VLSI areas? Because many students and the researchers are thinking that VLSI is now a little bit in a pause mode. It may take off. So, so what is your vision about VLSI, and followed by then wireless communication? Also, you are one of the pioneer in the world in the research in the wireless communication. So,
Things go in cycles. There's always a type cycle where people go, "Oh, software is the only thing that matters, and hardware and things like that." Actually, we are in a cycle now where hardware is actually in the upswing again.
oh wow,
It's getting more important, and the main reason for that is indeed things like IoT, biomedical interface, self-driving cars, all those type of things are built on innovative hardware platforms. So one can argue, well, Moore's law is ending and transistors won't scale anymore. I don't think that matters. Ultimately, what we're going to be doing over the next couple of decades is build more sophisticated devices that have more functionality.
exactly.
Basically, sensing capability, computing, communication, energy harvesting, storage, translation, all in smaller and smaller form factors and higher efficiency. The same thing we might see devices that directly communicate with biological tissue, where you interweave biology and physical elements together. So there's no question in my mind that hardware design capabilities are going to keep on going very strongly over the next couple of decades. It will be different.
Very nice.
It will be. It will not be the same thing about, hey, we're going to build digital circuits by putting gates together and so on and so forth. No, it's broader. It's much broader. But this is where innovation will reign. All right. Ultimately, we have to be creative on how we bring things together. Going in the third dimension is an example. Stack memory on logic and sensors, interweave them together. These are the type of things we need to think about. And that's going to basically require needs for new methodologies, new ways of production, manufacturing, testing, verification. All those type of things are going to be challenged, and we need to be innovative. So there's plenty of things to be done. I'm not worried about a dime about this at all. Actually, I'm a strong believer that hardware will shine in the next decades.
That's great. So my last understanding from you is that what about the wireless?
Okay.
I know we all know wireless 4Gs and 5Gs coming up, 6G research has started.
Right.
Other side IoT and multiple devices have come up with the wireless and all. It has to expand. But your vision with respect to wireless?
So, to me, wireless, we have a whole bunch of technologies. We're going to go to higher frequencies. We're going to go to higher densities. All those things will happen. To me, that's not the question anymore. I assume that we're going to have wireless connectivity at every possible range and things in that 10, 15 years from now. What it leads to, however, is a different vision of what computing are. Computers are going to be everywhere. The world is going to become a computer. A bunch of elements connected together through a variety of links, and it could be wired, wireless link, could be optical, could be a variety of things. But we have to look at the big picture. And the big picture is really a computing world, a world diffused with computing. And humans directly connected to that.
Mm-hmm.
We are part of that network.
I see.
We are an element of it. And that's why I don't think people say, well, computers will take over everything. No, humans are going to become part of that whole big picture. Yeah. That's what I'm saying. I'm basically saying wireless is, to me, a given factor. And yes, it will evolve and things like that. But the bigger picture is to understand what the system is going to look like.
Exactly. So, Professor, my last understanding from you will be your contribution in the low power.
Right.
A lot, particularly low power systems, communications.
Sure.
So, what is your low power means what you see, how low it will go? Do you think
right.
in so much IoT dust and swarm of devices you worked on? So, what is your, according to you, low power and where will it stop? Or?
So one way I've described my research over the years is how low can you go?
Yeah, exactly.
Right? Which is sometimes not the right things to think about. Yeah. But there's still plenty of opportunity, right? So today we know what the limits are, how deep you can go, and we're still, let's say, 4 to 5 orders of magnitude away from where we could be. Nature has found some ways to get closer. Again, if I look at biology, some of our cells, the synapses in our brain, work at about 2 orders of magnitude above the absolute limit. We should be able to get close to that. So there's plenty of opportunity to rethink computing so that we get actually more efficient. There's plenty of place to go. But it's not going to be your traditional, here's your deterministic computing instruction set style computing. Machine learning devices, things that are based on learning things will get closer because we don't require determinism anymore. We can reduce margins. So I think we have plenty of place to go, and it's going to be hard. It's not going to be easy, but there's definitely room to improve. If I look at nature figured it out, we should be able to figure it out too.
Great. So Professor, thank you very much.
My pleasure.
For your such an eminent person giving vision to the younger generation for the research on VLSI and wireless and low power devices, and in particular giving a bright future to the hardware people and the wireless people, that a lot of research is yet waiting for them.
That's right.
A lot of future for them. Thank you again, Professor,
My pleasure.
for visiting
Absolutely.
Bangalore and India.
Thank you.